I'm sure you can guess, I'm going to be talking about distributed training. My name's Matt. I work at a company called Exo Labs, where we started by doing inference on inference on consumer devices. We're a startup that let you do like inference AI workloads on consumer devices, like distributed like this. And we've started moving over towards doing distributed training instead. And so we've worked on a lot of things internally, but one of them is this idea called Sparta, which builds on the DeLoco paper out of Google DeepMind. So I'll start by recapping DeLoco and then tell you about what we did with Sparta. So if you think about data parallel training, in data parallel training, you have to, at every step, you do a forwards, backwards pass, and then every worker has to communicate the whole model, all of the gradients of the model at every step. And so what DeLoco does to reduce this communication is let these workers train independently on their own. They go down their own path for H steps. And then after H steps, they all synchronize with this outer step. This H number is really important. This characterizes how much you're reducing communication by. So if H is 10, then you're doing 10 times less communication than regular data parallel. There's, of course, a bit of a trade-off here, you can imagine, and typical numbers that are used for H are maybe like 30 to 100. So, for example, this prime intellect run or the scaling DeLoco paper, so if we think about what H does, if you increase H too much, so we can see here we increase H from 100 up to 10K, and the accuracy drops a lot, the performance degrades a lot, and this makes sense. If you let them train for too long on their own, the models will diverge, the devices diverge from each other, and so when you do this averaging step to communicate them all back together again, it ends up being destructive instead of collaborative. We can actually quantify this if we look at the correlation between models, the correlation between devices. So you've got two devices and they're allowed to train on their own. And you can see here, for this is H is 5,000, the correlation between the models goes down, 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 down. And at 5,000, they do this DeLoco outer step. And so the model, they then synchronize, and the model correlation between the two devices then spikes back up to 1. And this makes sense why DeLoco works so well with H is 100, because at T is 100, after only 100 time steps, your correlation hasn't dropped that much. It's only 99%. But of course, we want to be able to scale to higher H values than just 100 so that we can reduce the communication requirements. So this is where Sparta comes in. We said that the whole problem that we get with DeLoco is that the models drift too much. They diverge from each other if you let this H value be too high. And so what Sparta does is we take, at every step, we share just a small number of parameters between the models. You randomly subsample parameters from the model, and these get shared between the devices. And this helps us to reduce this kind of drift. It keeps the models in the same loss basin. They kind of are able to train in the same direction while still training pretty much separately. When I'm talking like a small number of parameters, I mean like really small, like 0.05% every 0.05% of the model at every training step. So it's not a large overhead. The amazing thing about Sparta actually is that these communications can be done asynchronously. If we do them asynchronously, if the sharings from one device to the next are actually delayed by a number of time steps, then it doesn't have any change in the performance of how Sparta works. The Sparta still is able to keep these models correlated, keep these models going in the same direction. As a result, we introduce Sparta, and it doesn't actually increase wall clock time for what we're doing at all. So, as I'm sure you can guess, we're now going to combine Sparta with DeLoco. So, we're running DeLoco. We do this this outer step here we're doing H is 5,000. So every 5,000 steps, we do this outer step, but we're also going to do these Sparta parameter sharings at the same time. And whereas for just DeLoco on its own, we see this like big drop in model correlation. If we include Sparta as well, it keeps them much more correlated, and they don't kind of drastically drop in correlation. The end result of this is that we can push H higher, of course. So here is our our test that we had at the start, where we compare DeLoco with H is 100 and H is 10K, and you see this big drop in performance when you increase H from 100 to 10K. And if we just we take this H is 10K case that doesn't do very well with DeLoco, and add Sparta in at the same time. So we just kind of use the spare bandwidth that you've got between these big synchronizations to share a few parameters from time to time. And this actually manages to beat the performance of DeLoco with just H is 100. I'll talk a little bit about some of the other things we're working on, because there are kind of some open problems and other things that we're excited about working on. One is scaling the number of nodes. We talked about, I talked throughout this whole presentation about scaling H, the number of communications that you have to do, how frequently do you have to communicate to reduce this bandwidth requirement. The biggest problem actually is being able to scale the number of nodes. If we can scale past these kind of limits that DeLoco and Sparta have, if you scale beyond n equals 8 or n equals 16, you get kind of diminishing returns from adding any more workers. It would be fantastic if we could scale beyond this. One idea that we have is that you lose a lot of information when you do this DeLoco outer step. You kind of you do this one step and you kill all of the averaging the parameters and you kill all of this diversity when you've got 8 separate nodes that have been trained in an ensemble, and then you kind of kill all of this information into just one node. So potentially there's more information that we can glean there if we keep them as an ensemble and don't do ever a full outer step, or maybe use other statistics such as the variance of the model. Variance between models. There's also a lot of things that we can do to improve Sparta. We wanted to keep Sparta as simple, kind of as dumb as possible, just to show that even in this really simple regime, you can actually get some fantastic performance improvements. There are kind of 3 axes to which we think that it can be improved. Currently, we're just averaging the parameters between models. So you just subsample these parameters across all of the devices and then average, and probably you could do something smarter there. We're also, when we're choosing what parameters to average, we're just sampling these uniformly. This is, again, not very sensible. There's many more beneficial ways that we could probably sample these parameters. The final thing is that we keep this p-value, the amount that we're sampling from the model is kept constant throughout the run. But we know from the same reason that we do a learning rate warm-up that training dynamics aren't the same at the start versus the end of a training run. So we could potentially schedule this number. Finally, we've got some customers that are interested in working on training different architectures. For example, different attention patterns or CNNs, and DeLoco struggles with architectures that aren't autoregressive transformers. So we're excited to find other algorithms that are a bit more agnostic to the architecture. So in conclusion, we introduced Sparta in this paper, but we also combined it with DeLoco and showed that we can reduce the communication requirements of DeLoco, reduce the synchronous communication requirements, and that, as a result, this reduces the wall clock time, whilst actually increasing the performance. The other thing to note is that we have a open source repo called ExoGym that lets you kind of simulate these distributed training algos on consumer hardware at home. So if you have one device, it can simulate having multiple devices within that. You can potentially play around with DeLoco and Sparta and all these things. Cool, thank you very much. I hope you guys have enjoyed this. If you want to find out more about what Exo Labs are up to, just give us a follow. We're also hiring if anyone's graduating soon. I'd be very interested to chat if you have any thoughts about the paper.
I was wondering, how do you choose at each step which nodes should be sharing parameters?
So at the moment, we're sharing between every node. So it's like
all nodes together.
Yeah. So you one master will pick, or they can either have the same seed, or one master picks what parameters they're going to be sharing. Mm-hmm. And they all sample those parameters, and then all reduce them amongst.
Got it. Thank you.
Yeah, I wonder why the basically sparse doesn't scale up more than N16 nodes. Because like the benefit from increasing like gap between communication is like 100x, right? So it can actually mean that you can scale like one order probably, but yeah, I'm not sure.
I'm not sure why it doesn't scale, other than the same reason of DeLoco, as you're kind of, when you average parameters, you average across every node, and so potentially if you have 16 nodes, for that one parameter, that parameter existing 16 times, and you kind of kill that information of 16 nodes into
So
one.
it's a communication bandwidth as well. So
yeah, I guess you scale the communication that you use scales linearly as well. But when I talk about doesn't scale well, I more mean like if we look at per step, what happens per step, then you add another node. If you use the same amount of flops but add one more node, then or double the number of nodes, then you kind of get diminishing returns from this extra node.
I see.
What kind of problems do Loco have with other architectures?
It just doesn't I don't know how to explain this. We tried it with a BERT style mask detention, and the training curve just kind of plateaued at a certain point and stopped learning. I haven't really looked more into, I don't know, Arthur would be the expert. I haven't really looked more into why this was the case, but I guess the algorithm was made for autoaggressive transformers. So,
on the topic of picking the parameters, did you try isolating to only specific parameters? So either only the MLP parameters or the embeddings or the
which parameters in the
which
model?
parameters you're sharing?
We haven't tried isolating. I did one experiment where instead of randomly subsampling, I just kind of enumerated through the whole model. And from that, you saw that the correlation plot that I had before oscillates with the same oscillation of how frequently you kind of stripe through the model. So I think that tells me like maybe the front layers versus the back layers have like relative importances. But yeah, I could definitely imagine something where you're doing fine tuning. Maybe you only touch the end layers or something like that.
Yeah, makes sense. Cool.
Could you explain what's the difference between Sparta and streaming DeLoco? Streaming is also like sharing a tiny fraction of the weights or updates. I don't remember exactly.
If I recall correctly, streaming DeLoco shares a third of the model each. Is that right?
Streaming DeLoco do share the outer update per subset of the parameters.
Yeah. So you'll pick 1 over like k of the model and share that. I guess Sparta is the kind of limit of that, where you share every step and you share a very small amount every step. But we also randomly sample which ones we're going to pick, as opposed to, I think, streaming DeLoco just enumerates. I think.
There's also that streaming DeLoco is sharing like the delta in the parameter space, while Sparta is the parameter itself. So it's slightly different properties.
Oh, yeah.
I noticed you basically have 0.05 of the parameters and around 2k steps, which roughly corresponds to like if you were to assume every parameter sampled once at 400%.
Exactly.
Did you try like having periodicity that is less than that 100%, either by increasing p and decreasing, or
Yeah, we tried a number of Sparta parameters. Like you can see that the performance is definitely dependent on how much you share. I think the nicest way to think about this in terms of, obviously, you don't want another hyperparameter to have to tune. The nicest thing to think about this with is like, you can have your bandwidth, and your bandwidth determines what P you're going to pick. You'll just do 1 over P, 1 over your bandwidth to like fit, okay, I've got this much bandwidth, I can afford to share this much kind of asynchronously during the training run.